Today we're doing section 14.3, partial derivatives.
Our goal in this video is to understand what the partial derivatives of a function represent and be able to find the partial derivatives of any given function. So if f is a function of two variables, its partial derivatives are the functions the partial of f with respect to x and the partial of f with respect to y, defined by the partial of f with respect to x is equal to the limit as h approaches 0 of f of x plus h comma y minus f of xy over h, and the partial of f with respect to y is equal to the limit as h approaches 0 of f of x comma y plus h minus f of xy over h. So notice the way we pronounce this is the partial of f with respect to whatever variable is in our subscript. So based on these limit definitions, the way we take the partial derivatives of a function is to hold one variable constant and differentiate with respect to the other variable. So for instance, in the limit definition for the partial of f with respect to x, y is staying constant and we're differentiating with respect to x. And then similarly for the partial of f with respect to y, x is staying constant and we're differentiating with respect to y. So find the first order partial derivative with respect to y of the following function using the limit definition of partial derivatives. So the partial of f with respect to y is equal to the limit as h approaches 0 of f of x comma y plus h minus f of xy over h. Okay, so we're going to take the limit as h approaches 0. We have to evaluate f of x comma y plus h. So 5x times y plus h minus 7x squared minus y plus h squared plus 3x minus 6 times y plus h plus 2. And then we have to subtract from that f of xy. So 5xy minus 7x squared minus y squared plus 3x minus 6y plus 2. And that's all over h. And we can simplify some of the terms here. So minus 7x squared, and then that would be plus 7x squared here. 3x, and then minus 3x. 2, and then minus 2. And we can simplify the terms that are left. So we have the limit as h approaches 0 of 5xy plus 5xh minus y squared minus 2yh minus h squared minus 6y minus 6h minus 5xy plus y squared plus 6y, and that's all over h. We can simplify again. 5xy minus 5xy minus y squared plus y squared minus 6y plus 6y. We can factor out an h from the terms that are left. So we have the limit as h approaches 0 of h times 5x minus 2y minus h minus 6 all over h. The h's simplify, and we can take the limit as h approaches 0 now. So we have 5x minus 2y minus 6. So the partial of f with respect to y is the function 5x minus 2y minus 6. Okay, so using the limit definition, we get a lot of simplification, but if we had to find both first order partials, this would take us a considerable amount of time. Looking back at the original function, we could have just used our derivative shortcuts to find this directly. Right? If we held x constant and differentiated y, the derivative of this term would be 5x. This term would be 0 since we're treating x as a constant. We have minus 2y here is our derivative, 0, minus 6, and 0. And we would get the same expression. Okay. Alright, so as far as notation for partial derivatives, if we want to represent the partial of f with respect to x, we can use any of the following notation. So we've seen this already. And then we have the stylized d, that's the notation for partial derivative. So the partial of f with respect to x. This is the partial with respect to x of the function f of xy. Partial of z with respect to x if our function is z equals instead of f of xy equals. And then this is the partial derivative with respect to x of f of xy. Okay. This notation is going to be used more in a later section. We can also find the second order partials of a given function. So if I have the partial derivative of f with respect to xy, that means I'm taking the partial derivative with respect to x first, then with respect to y. Okay? If you look at this notation here, we work from right to left, and the reason why is I really can write this as the partial with respect to y of the partial of f with respect to x. Okay, so when we see the partial derivative written in this notation, we're moving from the right to the left. We can take the second order partial with respect to the same variable, and that's what's given here, and you can see how we can simplify that notation as well. Okay? So what is the geometric interpretation of partial derivatives? So partial derivatives still represent a rate of change. So the partial of f with respect to x at the point AB, so here's the point AB in the xy plane, so then here's the point on the surface of our function. So when we take the partial of f with respect to x, we're holding y constant. So what we're going to do is find the trace of the surface in the plane y equals b. So there's the trace, okay, of our surface. And then the partial of f with respect to x then represents the slope of the line tangent to that trace line. Okay, this tangent line is parallel to the x-axis, so this represents the rate of change of the function at the point in a direction parallel to the x-axis. And then similarly, for the partial of f with respect to y at the point AB, we're holding x constant now. So if x is constant, let me use, I'll use blue again. Okay, here's our trace line when x equals a. Okay, and then we're finding the slope of the line tangent to that trace line at the point in a direction parallel to the y-axis now. Right, so the partial of f with respect to y represents the rate of change of the function at the point in a direction parallel to the y-axis. Right, so essentially we're finding the slope of the line tangent of trace lines, which we've looked at before. So looking at an example both algebraically and geometrically, we have f of xy equals 4 minus x squared minus 2y squared. Okay, so they've given us our graph, and then we'll talk about this in a second. So algebraically, if we want to find this partial derivative, the partial of f with respect to x, we're holding y constant. So if we're holding y constant, derivative 4 is 0. The derivative of negative x squared would be negative 2x, and the derivative of negative 2y squared is 0. And we're trying to evaluate the derivative at the point 1, 1. So the partial of f with respect to x at 1, 1 is negative 2. Okay, so here, there's our trace. Okay, there's our trace line, and I'll go over it in blue so we can see it. Okay, so there's the trace of our surface when y equals 1, and then we're looking for the slope of the line tangent to that trace line, okay, which does look to be negative. And this here, okay, we really can see the idea of finding the trace line because they've drawn in the plane y equals 1 for us. So there's the trace, okay, a lot easier to see here. And then we'd be looking for the slope of the line tangent to that trace line at that point. Okay? So then let's do it with the other direction, partial of f with respect to y. So algebraically, the partial of f with respect to y, holding x constant, so the derivative of 4 is 0. Derivative of negative x squared is 0. And then we have the derivative of negative 2y squared, which is negative 4y. At the point 1, 1, we get negative 4. So again, here's our trace in the plane x equals 1. Well, I can probably draw that a little better. Right, there's our trace. So then we're looking for the slope of the line tangent to that trace line at the point, and it does look like it has a negative slope. And again, we can really visualize it here. Here's the plane x equals 1. Right, so here's the intersection of the plane with the surface. So there's our trace line. There we go. That's better. And then we're finding the slope of the line tangent to that trace line at the point 1, 1. Okay? Alright, so find the first partial derivatives of the following function. f of xy equals y over x minus y squared. So we'll start by finding the partial of f with respect to x. So we're going to need the quotient rule here. So bot d top, so x minus y squared times the derivative of y with respect to x, so that's 0, minus top d bot, so that's chain rule, so 2 times x minus y to the first, derivative of the inside with respect to x would be just 1, over bottom squared, which is x minus y squared. So simplifying that, we would get negative 2xy plus 2y squared over, well, that should be to the fourth, x minus y to the fourth. Alright, and then we can take the partial of f with respect to y. Again, quotient rule, so bottom d top, so the derivative of y with respect to y now is 1 minus top times derivative of the bottom, which is 2 times x minus y to the first times the derivative of the inside with respect to y now, which would be negative 1 over bottom squared, which is x minus y to the fourth. So we would get x minus y squared minus 2xy plus 2xy actually, and then we would get minus 2y squared over x minus y to the fourth, and we can simplify that. So partial of f with respect to y is x squared minus 2xy plus y squared plus 2xy minus 2y squared over x minus y to the fourth. So simplifying here, we have x squared minus y squared over x minus y to the fourth, and we can keep going actually. Okay, so this problem actually works out nicely as far as our simplification goes, right? Because this is x minus y times x plus y. So over x minus y to the fourth. So x minus y, and that becomes 3. So the partial of f with respect to y is actually just x plus y over x minus y cubed. Okay, so that actually had a lot of nice simplification that occurred there. Let's look at a couple more examples. So find the first partial derivatives of the following function. F of xy equals the inverse sine of x squared y. So the partial with respect to x. So if you remember, the derivative of arcsine is 1 over the square root of 1 minus the inside, which is x squared y, then times the derivative of the inside with respect to x this time, which would be 2xy. So this would be 2xy over the square root of 1 minus x squared y. And then we can find the partial of f with respect to y. So again, derivative of the outer function is 1 over the square root of 1 minus x squared y. And then the derivative of the inside with respect to y now is x squared. So we have x squared over the square root of 1 minus x squared y. Alright, one last example to look at. Evaluate the first order partial derivatives of the following function at 0, 0. Okay, so try this on your own, and after you've evaluated it, play the video to see if you got it correct. Okay, so partial with respect to x of xy, derivative of tangent is secant squared pi y e to the x y times the derivative of the inside with respect to x, so that would be pi y squared e to the x y. So the partial of f with respect to x at 0, 0. So secant of 0 is cosine, the reciprocal of cosine. So cosine of 0 is 1. So that would be 1 squared. And then times 0. So that would be 0. And then the partial of f with respect to y. So that's secant squared pi y e to the xy times the derivative of the inside with respect to y now. So that's going to be a product rule. So pi e to the xy plus pi xy e to the xy. So the partial of f with respect to y at 0, 0 would be secant of 0, so that's 1 squared again. And then we have e to the 0 is 1, so we get pi plus 0. So the partial derivative of f with respect to y at 0, 0 is pi. Alright, so we covered partial derivatives. Hey, we talked about what they represent as far as geometrically and algebraically, their limit definition. Okay, so write down any questions that you have. Okay, we'll use the quiz and our questions to get into the problem set, and we'll go from there. Alright, enjoy the rest of your day, everyone.